To this second day of this very nice conference that Venkatesh and his colleagues at IISc have arranged for us. It's really nice. So thanks to them. And I
Correct.
have
You point out, it's all Venkatesh. It's all
okay,
Venkatesh. No
okay.
colleagues.
Yeah. I have the pleasure of introducing Arun Ram from the University of Melbourne, who is going to talk today about examples. This is his second talk in his series of 3 talks. For the format, I will try to follow what Amri did yesterday. So do type your questions in the chat box. But if that doesn't suffice, then we'll let you unmute and ask, because Arun says he doesn't mind being interrupted. Arun, over to you.
Thank you. Thank you very much. So I want to tell, somehow these talks are now in 3 different stories. They could be completely independent, even though I try to make some connections between them. And this one is a beautiful story of which there are many experts in this conference who know even much more than I do about this. But I became very interested in it for 2 reasons. One was because I saw the Pieri-Chevalier formula of Kato, Naito, Sagaki for the semi-infinite flag variety, and I thought that was fantastic. So I started to learn about level 0. And the second was what I alluded to yesterday, that non-symmetric Mcdonald polynomials appear as characters of these modules. So, so we have actually a survey paper on this subject with Finn and Yaping. This is the paper, which I have put the reference here at the bottom. And if for no other reason, maybe you would like to show it to your children to look at the pictures, because we are very, very proud of the pictures which we have made in this paper to try to illustrate these modules. And I think even if you look at this picture, at least for me, this is, I find it very exciting, the structure of modules. But I'll show you more slowly as we go. Let's see if I can blow up this. Okay, so the story is, I need to introduce fundamental weights for 2 Lie algebras. For G0, which I use Katz's notation for and G0 is finite dimensional, and then G is the affine, corresponding affine Lie algebra. So just to, the way that I think about it is that you are given, let's start with a Dinkin diagram, which in our case, because I'm focused mostly on SLN, so this is a finite Dinkin diagram. Let's make this a bit bigger. Diagram. For the finite dimensional Lie algebra, which is SLN plus 1, and it has nodes something like this. And then the affine Dinkin diagram is exactly the same. There's a very wonderful procedure for adding an extra node, which is 0 there. And so this is the affine Dinkin diagram. For the Lie algebra G. So this affine Lie algebra well, certainly if you are taking the point of view of Tomoyuki's talks, you want to build this as a loop Lie algebra, which means that I take my finite dimensional Lie algebra and then I create this loop Lie algebra. And then you will naturally consider a central extension, not tensor product, direct sum of that loop Lie algebra. And it's very convenient to add a derivation in order to make it Katsumudi. So this is the object that we're talking about. And I won't define the bracket. We don't need any formulas. So, but there is a bracket on this thing. And very importantly, because it's Katsumudi, it has a quantum, corresponding quantum group, quantum affine algebra, which I will denote by UTG. So the quantum group, I use T in this story instead of Q because I want the T to match Mcdonald polynomials. Match T in Mcdonald polynomials. And if you know already some of the weight theory for affine Lie algebras, then e to the delta or e to the minus delta is the Q in Mcdonald. But that's just to explain why I use UTG instead of UQG. So everything, all of my formulas will have T's instead of Q's if you're used to seeing Q's. Okay, so now what I want to do is I want to label these modules. I want to label, my goal is to label extremal weight modules, what are called extremal weight. I will define them after. It will take us a little while, but we will define them. And so for that, I need the fundamental weights. So I have fundamental weights for the finite Lie algebra. And these we might call, I call them omega 1, omega 2 up to omega n. And then again, following Katz, what I'm going to do is I'm going to add 1 lambda 0, and then I have lambda 1 up to lambda n. These are the fundamental weights for the affine Lie algebra. Weights. And they are related. So the relation is that for, let's say this way, for I between 1 and n, we have that lambda I is equal to omega I plus lambda 0. So if you're, I should say that if you're working in general type, there's a constant which can appear here, which is not necessarily 1, but in type A, this constant is 1, and so I want to think of it that way. Okay, so let me just draw the picture for SL2. So this is G0 is for SL2. So in that case, I have the omega, I have only one omega 1. So I have 0 and I have omega 1. And those form 2 omega 1, 3 omega, and so on. And then I have my lambda 0, which is the new weight, which is lambda 0, which is for the affine Lie algebra. And then there is a lambda 1 here, and lambda 1 is omega 1 plus lambda 0. So if I go omega 1 plus lambda 0, then I end up at lambda 1. Okay, so now, of course, I can take 2 lambda 0 is here. And if you think about it, 2 lambda 1 is here, and 3 lambda 1 is here. And so I get this cone, which is positive linear combinations of the lambdas. So that set I will call HZ star positive. So this is the non-negative linear combinations of lambda 0 up to lambda n. And then I have another set, which is the 0 part of H star, which is the non-negative linear combinations of the omegas. If I was, so I guess I should have made these all green. To match my notation there. And then we have finally a set consisting of the negative linear combinations of lambda 0 up to lambda n. So if you think about it, then negative lambda 0, lambda 1 is here. And so I get another cone which extends this way. So I have a red cone on top and a blue cone on the bottom, and then this line, green line sticking out. And the statement is that the extremal weight modules, I have not defined them yet, but modules. Actually, let's make two statements just for fun. So if I just take the finite Lie algebra, this is in bijection with the 0 part. And so for each one of these green dots, I have a module which maybe I'll call L circle lambda. And then if I go to the affine Lie algebra, then I have extremal weight modules. For the affine Lie algebra. And now I take all three sets. I take the positive cone union the 0 line or the 0 plane lattice union the negative. And you have lambda here corresponds to an extremal weight module, which I will call L lambda. Now it's very special that in type A, and not in type A, in finite type, this extremal weight can be replaced with irreducible finite dimensional. These are the same thing in finite type, but this is definitely not equal to irreducible finite dimensional. And it's also not equal to irreducible highest weight. But it is, all of these modules are integrable. so yes, so this is a subset. Let me write it this way. This is a subset of integrable modules. Okay, and in some sense, well, the way I've said it, we just have to take subset there. Okay, so I have this picture. In fact, this picture must also be in this paper. Let's see if we can find it. yeah, of all the indexing set for my integrable modules. And I think of, if you ask me, okay, think of a module, I think of one of these dots, and each one of these dots will index my modules. So these red dots, these are in fact the irreducible highest weight dominant highest weight modules. So these are the dominant integral weights. And these blue modules down here, the extremal weight modules, are the irreducible lowest weight anti-dominant weights. And if you are in affine type, your highest weight module is not a lowest weight module. It really is so there's a beautiful picture for what these, you can see that in affine type, the highest weight module looks like a parabola like this with a something at the top, so it makes it highest weight, but it extends infinitely down, infinitely low downwards. And on the other hand, the lowest weight module has bottom, something at the bottom, and then it extends infinitely upwards. See, in fact, in SL2, it's even more clear because you see these parabolas which create the downward. These are the highest weight modules, and then the lowest weight modules are these parabolas. And so in the middle, these level 0 modules, they have this tubular shape, and that's what we're going to produce some of those today. Okay, so that gives you a feel for what my world is. My world is this world of integrable modules, and that's how we label them by this collection, by this collection of weights. All right. So now let me tell you what the quantum group is. So the quantum group, so generators and relations for the affine quantum group.
Arun, can I ask a question, please?
Yeah.
You have said that these modules are integrable, but is there a characterization of these as something?
Yes, they're characterized as the extremal weight modules.
Okay.
But I haven't defined that yet.
Okay,
so that
right. Okay, yes.
I mean, these are the universal modules which are generated by extremal weights. But we'll get. I'll explain a little bit better.
Right.
Fully,
Okay.
If you fully, you have to read Kashiwara. But I will explain a bit better. But first, let me set up the quantum group. So the quantum group has two presentations. The first one is the Katsumudi presentation. And this one has generators, which are C to the plus minus a half, and D to the plus minus 1. And then I have K0, K1, K2, up to Kn. You remember that my Dinkin diagram, so there's one of these for each node in this Dinkin diagram, and I have a 0 there. And these Ks are invertible. And then I have additionally E0, E1, E2, up to En, and F0, F1, F2, up to Fn. And these satisfy relations, which usually we don't write, but I copied them here just in case you want to look at them. But I suggest you don't look at them because they're really quite horrible. And unless you have played with Serre relations quite a bit, they're just unpleasant. There's a lot of relations to remember, and you slowly get some feel for them. So presumably, because this is a bit unpleasant, Drinfeld made a wonderful comment in his paper. He says, fortunately, UTG has another presentation. So this presentation is, of course, we saw it yesterday as well, but this is the loop presentation. And it has generators. So I will keep the C to the plus minus a half, and I like to keep the D in there. I may make a comment about that later, because there are good reasons to throw it out in a wise way, but in principle, it's still there. Now I'm going to throw away K0. So I'm going to start only with K1 up to Kn. So this is really trying to take somehow just this finite Dinkin diagram. But now I'm going to add some more generators, x1r plus up to xnr plus for r in Z. And then I'm going to have x1r minus up to xnr minus for r in Z. And then I'm going to have ES1 up to ESN for S in Z not 0. Okay, so these are the generators for the loop presentation. So before, as you can see above here, I had 3n plus 2 generators, 3n plus 1 plus 2, 3 times n plus 1 plus 2 generators. And now I have 3n times infinity plus n plus 2 generators. So I have many, many, many more generators. So, so then you look at the relations, and you see that these are the relations, and they don't fit on one page. They fit on 2 pages, 3 pages. So now I have 3 pages of relations for you to learn to work, right? And so you begin to wonder, why did Drinfeld think that this was a good idea? Because to me, when I saw, for the first 10 years that I saw this, I thought this is crazy. I'll never work with such a thing. It's so horrible and complicated that you can't possibly do anything. But there's one formula I want to copy here from these relations. And that is this formula, which says that the exponential of the sum L in Z greater than 0 of PLI divided by the T analog of L times Z to the L is equal to 1 plus the sum over S in Z greater than 0 of ESI Z to the S. Where here Q analog of L is T to the L minus T to the minus L divided by T minus T inverse. So this is just some conversion. Oh, and in fact, I was going to get the book, the Mcdonald book, because this P and this S, unfortunately, Drinfeld didn't use P and S, and neither did anybody else, it seems. but these really should be P and E, P and E. It really should, in fact, let me get the book. I have to get the book. This is the book. Right? This is the book, because this book tells you that P is a power sum symmetric function and E is an elementary symmetric function. And if you look at this P and this E, then there's a relation here which says that, that the bracket of PSI and PRI bracket is 0. Unless you bracket PS with P minus S, it's 0. So if you bracket P2 with P3, the bracket is 0. So there's a lot of commutativity here. And then there's some constant, and then some constant, some constant. So that's a good thing, because this thing is a Heisenberg. It's a big Heisenberg, but it's a Heisenberg sitting inside the affine quantum group in a very concrete way. And so this is going to save our lives. This is really what I want with this object. Okay, so maybe I'll take these things away, and let's just have a small summary. So this is a small summary of our presentations of our quantum group. Okay, so next I want to now tell you what this extremal weight module is. So this is a presentation of the extremal weight module L lambda. And let me do it just for lambda at level 0. Just to be a bit concrete. So I'm looking at this, one of these green dots. So if I'm looking at one of those green dots, it means that my lambda is m1 omega 1 plus mn omega n, with m1 up to mn being some non-negative integers. Okay, so there are two presentations. One is the Katsumudi presentation.
Arun, I have another question.
Yeah.
You haven't told us what the PSIs and PRIs are in terms of the generators. Presumably they were included in the sheets that you went through.
So actually this identity, it completely defines the P's in terms of the E's.
Okay, right. Okay, yeah. Right. That's the definition. Okay, got it. Thanks.
Yeah. Okay, wonderful. So this Katsumudi presentation is Kashiwara's presentation for this. Kashiwara is the one who wrote these down very early. So this is has generators. So the generators are UW lambda for W in W. So I need to make a comment about this here. So here's my picture. So what I'm going to do to make these generators is I take one dot. This is U lambda. And then I'm going to move that around to create more dots. So this is US1 lambda, US2 lambda, S1, S2 lambda, U, S2, S1 lambda, U, S1, S2 lambda. And then I'm going to create even more dots because I'm going to use the affine Weyl group. This thing is the affine Weyl group. So in fact, if we look at this picture of this tube-like thing, all of these black dots are generators. And in order to know what these black dots are, you really must understand the orbits of this affine Weyl group. So the orbits correspond to, are in bijection, give the generators. This module. And so I think it's really useful to look a little bit at the orbits. So this is the picture for SL2 of the orbits of the affine Weyl group. So you can see that these are really the levels, as if you are going up and down an elevator. You go up and down the lift, you go to higher level, and then on a given level, you can see that the orbit is a parabola. On a given level, the orbit is a parabola, and this is the orbit of the affine Weyl group. So in fact, if I'm looking at, you can see there are dots along the edges. Maybe I have a better picture here. Yeah, you can see the dots on the edge of this parabola. These are the generators for my module, all of these black dots. And they come from this parabola. But if I'm in negative level, the parabola is shaped the other way, and I have generators, black dots all around the parabola. But if I'm in level 0, something very interesting happens. You can see that there's a singularity there. And in level 0, you have this tube. Just naturally appears, this tube appears from the affine Weyl group orbit. So even just looking at the affine Weyl group orbits this way, I already see the structure of the black dots, which are the generators of this module. Okay, so that's the generators. And then we have to write the relations. The relations are as follows. So because I'm working in level 0, c to the 1/2, acting on one of my generators, it just fixes it. And ki acting on this, this vector uw lambda picks off the alpha I portion of the weight of that. So it gives me a constant. So these are weight vectors. And if you don't know the notation for root systems, that's okay. Just ki acts by a constant, which we know exactly on this weight vector. And then the next condition is that if that constant is a positive integer, then ei acts on the vector to 0. So it's acting as if it was a highest weight vector for that direction. And fi to the correct power must take it to its corresponding dot. So these dots are all around the cylinder, and you can move them around by the fi's, go from one black dot to another dot. And then similarly, if this integer is negative, then it works exactly the other way around. Fi acting on UW lambda is 0, and EI to the correct power will take you to the next black dot. So you can move around all these black dots. And these are the relations now for a UT module. So this defines a module for the quantum affine algebra. And this is the module that we call L lambda. All right, so it's a very explicit module at this point. But of course, it couldn't be more wonderful that there's another presentation for this this module using the loop generators. So in this presentation, there's only one generator, U lambda. So I don't need all those black dots anymore. I mean, here I was working with all of these black dots, an infinite number of black dots, and then generating the module. And now I just take one. That's it.
Arun, could you remind us once again, there's a question. Lambda belongs to H, the, where did you start from lambda?
Lambda, for this story that I'm telling, this is going to be level 0.
Right, okay, thanks.
Yeah, very good. Okay, so what are the relations for this module? So first of all, it's level 0. So that means that, that C acts on U lambda by the identity. And it's weight lambda, so that means that Ki U lambda is T to the Mi U lambda. Like you said, I'm taking lambda to be M1 omega 1 plus Mn omega n. So it's a weight vector with this specific eigenvalue determined by these numbers. And then I have these loop generators, X plus, X minus, and E. And how do they act? So they act in the following way. So XIR plus U lambda is 0 for all the I's and all the R's. So in the loop presentation, it looks like this vector is a highest weight vector. It's killed by all the X pluses. And then if I look at the elementary symmetric functions, they also kill, provided that your S is bigger than Mi. And I also have negative elementary symmetric functions. And they also kill, provided that your S is bigger than Mi. So in some sense, this is a much nicer presentation. That's it. That's the presentation. I specified exactly which generators have to act by 0 on this generating vector U lambda. And it produces this, this module. So let's see if I can have the summary here, and that will yeah. So here I wrote the summary of these presentations of this module. So now let's look at one of them. Yeah, so this is an example. Maybe I should actually write it out so that it doesn't go too fast. Let me write it out. and none. So this is the example of this picture that we are looking at here. So I'm going to write down L omega 1 plus omega 2 for UTSL3 hat. All right. So it has vectors in it. Let's call it V theta, V alpha 2, V alpha 1, H alpha 1, H alpha 2, V negative alpha 1, V negative alpha 2, and V negative theta, and H theta. Okay, but that's not quite the whole story, because so what I'm writing down, I should have said here, what I'm writing down here is a basis. I'm creating a basis for this model, a basis over the complex numbers. Because each of these V there are more symbols by epsilon 1 to the R1, epsilon 2 to the R2. Epsilon 1 to the R1, epsilon 2 to the R2. And this is here R1 and R2 run over all integers. So I have epsilon 1 to the R1, epsilon 2 to the R2. Epsilon 1 to the R1, epsilon 2 to the R2. Epsilon 1 to the R1, epsilon 2 to the R2. Epsilon 1 to the R1, epsilon 2 to the R2. Epsilon 1 to the R1, epsilon 2 to the R2. Epsilon 1 to the R1, epsilon 2 to the R2. So it's a very beautiful module. It's only 9 infinity dimensional, because there's in fact infinity squared, right? This if we're going to count the number of basis vectors, this is infinity squared. And the total number of basis vectors is 9 infinity squared basis vectors. All right, so that's what this module looks like in terms of just its size. So it's trying to be a huge model. Here I've written down the same thing again. And now I want to write down this action to what is it? So I'm going to ignore the epsilon 1s and epsilon 2s. So let's pretend for a moment epsilon 1 is some number A1 and epsilon 2 is some number A2. All right. And I'm going to try to write it. Now it's only a 9-dimensional model. I just squashed it. I've taken away all of this periodicity of these epsilons are moving it up and down, and I squashed it. And now the action, well, I've drawn the picture here, but let's draw it again. There are some blue edges that go like this. Those are the blue edges. And then there are some purple edges that go like this. And you say, but this is exactly the adjoint representation of SL3. It's 8-dimensional, except there's this lonely guy stuck by itself that didn't get the ordinary. So we have to take care of that. And we take care of that with some red edges that go like this. But then there's also a red edge here. And a red edge here. So this is the structure of this module if you look at it in the Katsumudi action. And you can see that it's very periodic. It's trying to be very circular. It's going around. If there's any theme for my lectures for this week, it's that periodicity. You will have periodicity in some fashion. But it's much better, in fact, to keeping track of the epsilons a little bit. So here I have written.
Ask a question.
Yeah.
So about F0, do you understand correctly that the finite weight is minus theta and the weight with respect to the affine shift d is 1? Is that right?
Yes, I think that's right. Let me draw the next picture and then you check if it matches what
Thank
you
you.
said. I think that what you said is exactly right. That's how yeah. So here I'm looking at all of those basis vectors which satisfy.
Was there another question? Go ahead, please.
Yeah, please ask.
So as a as a G model, it looks like okay, the restriction of the affine Demasur. Is it coincidence or?
So
So
in order to talk about restriction of affine Demasur, you have to tell me Demasur inside of what thing? And this is for me a very.
This is it looks like V theta directs some one dimensional.
That's right.
It's in our notation it is D1 theta, I guess.
So this is L0 omega 1 plus omega 2 plus L0 0 as an SL3 module.
Yeah.
That's right.
If we take SL3 affine and then there, so I forgot exactly. So we can take the transformation at minus theta and then take lambda naught.
That's right. So there's an amazing thing, and that is that if you take a Demasur module inside this level 0 thing, which I have built, this infinite level 0 thing, and then you tensor that level 0 module by L of lambda 0, then it becomes level 1. Mm-hmm. And the Demasur module inside the level 0 thing becomes a Demasur module inside the level 1 thing. So you can always shift Demasur modules into higher levels just by taking tensor product. But this is somehow, it really came from level 0. It didn't really come from level 1 in my philosophy.
Okay.
Yeah. Okay, so let's draw the picture of what this looks like in this infinite dimensional setting. So what I'm doing is I'm keeping track of the degree in epsilon. So this is the degree, epsilon degree. So epsilon degree 0, epsilon degree -1, epsilon degree 1. And then this action of the red edges goes like this. So you see, it's moving things exactly in this weight, adding the weight theta, but it's as Yevgeny was saying, it's changing the degree of epsilon, which is the weight delta. So it's actually moving you downwards and twisting you around this cylinder as you progress. And yeah. Okay, so that's what these modules look like as modules. And there's a very important thing which we did is here we said pretend that epsilon 1 is A1 and epsilon 2 is A2. So this is an important, extremely important tool. Maybe we call it trick or tool. And so that tool has a name. Let me see if where did I write it? Well, let me just write it down if I have room. Okay, so the way I like to say it is that the global vowel module is the same as the extremal weight module. So historically, when they were first defined, there were two different things defined, and it wasn't completely clear that they were the same. But eventually, Nakajima's papers explained quite clearly that they are exactly the same. That there are different presentations to look at, but they are the same module. So that's this infinite thing. But then I can always do this technique, is that if I let A1 and A2 be numbers, complex numbers, then the local vowel module at this point, A1, A2, is the global vowel module, is the extremal weight module. So we should call that the extremal weight module. But with the elementary symmetric functions specialized at A1, or the elementary symmetric function. However many elementary symmetric functions you have acting on your module non-trivially, you specialize those to numbers. And that's the local vowel module. And the local vowel module takes this big cylinder and shrinks it, smashes it to a 9-dimensional module. That's what happens there. Okay, let's see. So in my picture here, let's look at, I want to show you where does the Mcdonald polynomial come. So this was our Mcdonald polynomial, and that we computed yesterday, otherwise. And you can see it has 9 terms. 1, 2, 3, 4, 5, 6, 7, 8, 9. And one of them has a Q. And this comes exactly from the following game. So let's start with this minus theta here. And let me go upward from minus theta. I go upward. 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 Up. So I build these 6 terms, and then I could go up from this to build the only one that's these 8 terms, and then I build the only one that was missing. And you can see that the one that was missing, in order to get to it from this negative theta to get to this theta, I can't get to it on the same level. I have to change the level. I have to change the height in terms of the epsilon degree. And that's exactly the reason why there's a Q in front of this term of the Mcdonald polynomial. So this Mcdonald polynomial, we constructed it by intertwiners, and these intertwiners exactly correspond to these upward motions in this crystal. And then there's this very important one that changes our degree in epsilon, and that's where the coefficient of Q comes from in these Mcdonald polynomials. Okay, actually I think instead of, oh no, I do want to say this thing. So this is the same module. This is in the loop presentation. So there are 2 presentations of this module, we remember. One is the Katsumudi presentation, and the other is the loop presentation. And this module in the loop presentation, loop action, has a basis of eigenvectors for the elementary symmetric functions. But I put eigenvectors there in quotes. It means that they're not really eigenvectors because they might change the epsilon. So they keep the same vector, but they are allowed to, the eigenvalue could involve epsilons. Eigenvalue involves epsilons. But when you draw the picture of this, the picture is very nice because the picture just shifts these vectors. They become eigenvectors for the action of EIS. And it shifts up and down like this. And so the loop action makes the module really look like a 9-dimensional module for finite SL3. And then the Heisenberg action just moves me up and down, directly up and down this tube. So the Heisenberg subalgebra is very controlled in terms of this 9 plus the periodicity. Okay, so I think I stop there because that's a good point. If I go ahead, it'll take too long. So
let's thank Arun for an excellent lecture, which is true to his form. So. Questions, anybody, please?
So
Yes.
Go ahead, please.
Yes. Could you please say a few words about positive and negative levels?
about positive and negative levels.
Yeah.
So in positive level, the modules look like this somehow. And then you have extremal weights. So you might have an extremal weight here, lambda. And then this is S1 lambda, S0, S1 lambda, S1, S0, S1 lambda. So you get something like this. And I forgot S0 lambda. I could have included an S0 lambda and then S1, S0 lambda. And then the action of the F's is going like this. So F1, 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 F1. And the action of the F0s is going like this. So this gives you a feel for how you have a highest weight. This is my vector U lambda here is my highest weight, and then it's going completely down negative. But it's still an extremal weight module because it's generated by the extremal weights. What else did you want to know about it?
So just in the, but you said these are not irreducible modules, right?
In positive level, they are irreducible.
Ah, they are. Okay, good.
Yes.
Good.
Yes.
Okay, thank you.
Arun, I want to ask you a question. To summarize, you have said that the specialization at t equal to 0 of the Mcdonald polynomial, which had 9 terms that you showed us yesterday, is the character of the local while module. Is that correct?
That's right. Yeah.
Okay. So if you don't specialize that t equal to 0, does that capture something about the global while module?
Well, I mean, even the specialization at t equals 0 captures the structure of the global while module, because the specialization at t equal to 0 is this blue part. And if I repeat this blue part infinitely up and down, then I get the full global while module. So in fact, the full character of this thing can be written of L lambda is you take the non-symmetric Mcdonald polynomial at t equal to 0, and then you multiply by the character of Rg lambda, and Rg lambda is exactly the Heisenberg modulo, that those relations that I had, that EI S is equal to 0 for S not in the interval between negative mi and mi. So in fact, we saw this ring in Denis's talk yesterday, that he was taking some ring of symmetric functions in some number of variables. But he had a finite number of variables. And so what I have done here is exactly killing equivalent to choosing a finite number of variables in each part of your Heisenberg. So this is a quotient of a Heisenberg algebra. And if you take the character of that, you get exactly the periodicity. And then if you multiply it times the 9 dimensions from the blue part, that's this Mcdonald polynomial. So.
Thank you. I have more questions. So this specializations A1 and A2 complex numbers, should they avoid certain things, or any numbers are okay?
So that gets to what you were asking about the universality of this guy. So indeed, if you specialize A1 to certain places, then the local while module is not simple anymore. If A1 and A2 are generic, then L lambda is simple. L lambda is simple. L lambda specialized, local, L lambda local is simple, but not in general. So if not, you need to find its head. What is its composition series? Well, this is a big subject. It's and I certainly don't know much about. I mean, I know small things, but I don't have any big statements to make about what the composition series of this is. I mean, certainly people in this conference know much more than I do about that question.
I have one more, possibly because a question which I'm asking, possibly because I didn't hear you properly. So you call these generators EIs as elementary symmetric functions, right? In the loop presentations, you had both the power sum symmetric and the elementary symmetric appearing. Is that correct?
Yes, I only need. I mean, these E's, they generate some ring of symmetric functions, and then I can change whichever to. If I want to change from E's to P's, I can, or I could change to H's, or I could change to Schur's, or.
Right. But then in the specialization, you were specializing those epsilons to AIs, right? That's what you were doing.
That's right.
But
But I didn't. Yeah, go ahead.
I thought at some point you said the epsilons were also symmetric functions. Maybe I heard you wrong. Epsilons, did you say that, or did I hear you wrong?
Well, they're symmetric functions in some imaginary variables. I mean, they at the moment they're just symbols e's and p's, which satisfy the ordinary interrelations of symmetric functions. But of course, I could introduce those imaginary variables, and that's what people normally do, to make them actual symmetric functions in some variables that are available.
Okay.
I have a question. You said that you changed the variable in the UQ to a T to match it up more precisely with the Mcdonald case, with the T which appears in the Mcdonald polynomial. So, but I mean, in some sense, we never saw the T. So okay, let me try to make this more precise. So, for example, is the Mcdonald polynomial at q comma t somehow related to the character of these local or global y modules, with t sort of coming from the quantum groups T? Is that a...
Yeah.
Does that make sense?
Question.
Hello, Arun, are you there? Hello, am I audible, Venkatesh?
I can hear you, yeah, but we seem to have
okay. It
lost
just
Arun.
seems like Arun is.
I'm back.
Okay. Sorry, Arun, maybe you could start from the beginning answering Vishwanath's question, because we lost you.
Oh, okay. I think your question was, does this elementary symmetric, does this Mcdonald polynomial Q and T have any real meaning?
Right, in this context with, yeah.
And the answer is, I don't know. I only after I specialize T to 0 can I connect to the crystal or to the character of the affine Lie algebra module.
So, I mean, your use of the variable T for the quantum group was more to disambiguate the Q rather than to...
That's right.
Okay.
The Q is definitely the e to the delta. It's
Okay.
definitely the imaginary root.
Okay. But we don't know what the T is.
We don't know what the T is.
I see. Okay.
Let's thank Arun once again for his inimitable presentation.